The Great Pyramid required moving 2.3 million stone blocks. Ancient builders achieved this impossible task, not with alien technology, but with logistics systems of breathtaking sophistication. By the end of this exploration, you will understand the hidden genius that enabled history's greatest constructions and what it teaches us about solving modern problems. We will uncover how planners moved 50-ton stones for miles and coordinated thousands of workers with mathematical precision. What forgotten lesson from our past most challenges your view of ancient innovation, 2.3 million stone blocks? That number is almost impossible to grasp. To put it in a modern perspective, it is like building 30 Empire State Buildings, but without any of the machinery we take for granted. This was not a project of brute force alone. It was one of the earliest and most sophisticated examples of supply chain management the world has ever seen. Think about what that required. Planners had to coordinate the arrival of materials from distant quarries, manage a rotating labor force of thousands, and schedule everything around the annual flooding of the Nile, which was both a challenge and an opportunity. This system did not appear overnight. It evolved over centuries, with each generation of Egyptian builders learning from the last, refining their techniques, and adapting to new constraints. The true marvel was not the physical strength of the workers, though that was immense. It was the mathematical precision used to calculate angles and weights, the astronomical knowledge to align structures with the stars, and the social organization to house, feed, and motivate a workforce the size of a small city. When you understand this foundational layer of planning, you start to see these ancient wonders not just as piles of stone, but as the peak of a hidden logistical empire. And it all began with the very first step, the moment a block was chosen from the earth. The Nile's annual flood was not a disaster to be endured, but a season of immense opportunity. As the river swelled, it transformed the arid landscape into a web of liquid highways, capable of bearing burdens that would crush any cart. This was the secret to moving the pyramid's core building blocks, massive limestone blocks quarried far to the south. The Egyptians did not just use the river, they mastered it, constructing a fleet of specialized cargo boats. These were not simple rafts. They were engineered wooden giants, designed to use the principle of buoyancy to make the impossible seem effortless. A single vessel could carry the weight of a 500-ton obelisk, floating it down river as if it were a leaf on the current. This was logistics on a grand scale, turning a natural cycle into a scheduled delivery service. This reliance on water was a global phenomenon. The Roman Empire wove the entire Mediterranean Sea into its supply chain, using vast merchant ships to carry marble from quarries in places like modern-day Turkey and Greece to construction sites from North Africa to Britain. In China, successive dynasties invested centuries in carving out elaborate artificial canal networks, creating dedicated aquatic roads for moving mountains of stone and timber. These waterways became the undisputed backbone of ancient logistics. The real genius was not just the boats themselves, but the entire supporting system. Engineers developed clever loading mechanisms using ramps and counterweights, and they built dedicated docking facilities to streamline the transfer of materials from ship to shore. This was a complete, optimized system designed to minimize effort and maximize results. It demonstrates a profound truth about these ancient planners. They possessed a deep understanding of their environment and chose to work with its rhythms, not against them. They saw a flooding river not as a problem, but as a partner in their ambition. Yet, what happened when the final destination was far from the water's edge? How did they manage the last crucial leg of the journey across solid ground? The answer lies in another set of brilliant innovations that took over where the rivers left off. The final leg of the journey, moving a 50-ton block from the riverbank to the heart of the construction site, presented a monumental challenge. Without the buoyancy of water, every ounce of weight had to be overcome by sheer ingenuity. The solution was a symphony of coordinated effort, with thousands of workers dragging massive stone blocks on specially prepared roads. They used wooden sledges, not carts, and constantly placed and repositioning wooden rollers underneath the sledge to create a moving pathway. To further reduce the immense friction, teams would pour water or a slick slurry onto the path ahead, turning sand into a surprisingly effective lubricant. This was not brute force, but a carefully managed application of physics. Overcoming the limitations of pre-wheel technology required such clever adaptations. The Egyptians perfected this method for hauling stones across desert terrain, their sledges pulled by large, organized teams in a rhythmic, coordinated pull. This land-based system was a logistical marvel in itself, demanding not just strong backs, but careful planning of the route and the management of the workforce. The invention of the wheel eventually revolutionized land transport, of course. In Mesopotamia and later civilizations, ox-drawn carts emerged, capable of moving heavier loads over much longer distances. But this new technology demanded a new kind of infrastructure. Road construction became essential. The Romans, masters of empire building, understood this better than anyone. They constructed extensive networks of straight, durable roads that enabled the efficient movement of construction materials, troops, and information across their vast territories. These were not mere dirt paths. They were sophisticated engineering projects, built in layers for drainage and durability. These land routes required careful planning of rest stations for animals and workers, gentle gradients to manage the back-breaking effort of climbing hills, and dedicated maintenance crews to keep transport flowing smoothly year-round. This coordination between the road builders and the material transporters represents an early form of integrated logistics planning that maximized efficiency. It was a complete system where every element from the road surface to the resting post was designed to support the movement of weight. This seamless integration of water and land transport created a powerful network. But these physical systems, no matter how brilliant, were ultimately powered by people. The true engine behind every stone moved, every sledge pulled, was the human element, the vast and complex organization of labor. Coordinating 20,000 skilled workers required a social blueprint as sophisticated as any engineering plan. These were not slaves driven by whips, but a highly organized labor force working in rotating shifts, a system that would be recognizable to any modern project manager. At the Giza Plateau, this human engine was structured with remarkable precision. A clear hierarchy of overseers, scribes, and foremen directed specialized teams, each with a distinct role. Quarry workers expertly extracted the stone, transport crews maneuvered the heavy sledges, ramp builders maintained the vital inclined pathways, and the final construction teams positioned each block with exacting care. This division of labor was not just about assigning tasks. It was about cultivating expertise, creating a workforce where each individual's skill made the entire operation more efficient and productive. The remains of worker villages near the pyramids offer a stunning window into this logistical support system. These were not temporary camps, but structured communities with bakeries, breweries, and infirmaries, all designed to sustain a massive, permanent workforce. The scale of provisioning was staggering. Every day, thousands of loaves of bread and vats of beer were distributed as standardized rations. a system for feeding a small city that prefigured modern supply chain management. This careful provisioning reveals a profound understanding that a well-cared-for worker is a productive worker. It was a monumental investment in human capital. This vast labor pool was also incredibly flexible. The workforce ebbed and flowed with the seasons, drawing heavily on agricultural workers during the inundation of the Nile, when farming was impossible. This created a brilliant, cyclical labor model that prevented idleness and provided a ready source of manpower for the state's most ambitious projects. The entire operation, from the quarry to the rising pyramid face, was a testament to social innovation. The true foundation of these ancient wonders was not just stone and mortar, but the intricate organization of people, a system that housed, fed, and motivated thousands toward a common goal for generations. Yet, none of this human effort would have been possible without a parallel system, one that ensured a relentless flow of supplies to the bustling worker villages and the construction site itself. The true scale of this endeavor becomes clear not in the stone but in the bread. Every single day, the sprawling worker city at Giza required tens of thousands of loaves and vast quantities of beer, a logistical challenge that rivaled the movement of stone itself. This was not a simple matter of handing out food. It was a meticulously planned supply chain that operated years in advance, a silent, parallel project running alongside the construction. Agricultural estates across Egypt were dedicated to producing the grain that would become the daily rations for this army of laborers. Scribes kept detailed records on papyrus, tracking the delivery of fish from the Nile, grain from the farms, and even the pottery vessels from specialized workshops needed to store and distribute everything. This was an early form of just-in-time delivery, a system designed to have supplies arrive precisely when needed to avoid the catastrophe of spoilage in the desert heat. The most critical supply, however, was water. In a desert environment, keeping thousands of workers hydrated was a monumental task in itself. Engineers addressed this by digging deep wells, creating rainwater catchment systems, and organizing teams of water carriers whose sole job was to ensure a constant, life-giving flow to the workforce. This profound attention to human needs reveals a crucial insight held by the ancient planners. They understood that a well-fed, healthy worker was a productive worker. The entire provisioning operation, with its careful accounting and coordinated deliveries, was not an afterthought. It was a strategic investment, as vital to the project's success as the quality of the limestone. This intricate dance of sustenance paved the way for the next layer of innovation, the physical tools that turned human effort into monumental achievement. These tools transformed human muscle into a force of nature. A simple lever, a length of rope, or a greased wooden roller became a mechanical multiplier, allowing a small team to shift weights that would otherwise be completely immovable. The true genius was in the application of physics, not just the tools themselves. An inclined plane, for instance, is just a ramp, but by using one, workers could trade the impossible vertical lift of a stone block for a longer, manageable pull along a gentle slope, distributing the immense effort over a greater distance. This is mechanical advantage in its purest form, a principle understood intuitively by ancient engineers long before it was formally defined. Different civilizations developed specialized toolkits based on their unique environments and materials. The Egyptians, masters of stonework, perfected copper chisels and stone hammers for quarrying, while Roman builders, with their access to superior iron, created more durable picks and saws that could shape the hardest granite. But the real breakthroughs came with compound tools. The invention of the pulley, for example, revolutionized lifting. By threading a rope through a wheel, a single person could redirect their pulling force downward, using their own body weight to help hoist a load. Multiple pulleys used together created a block and tackle system, dramatically increasing the lifting power available from a small team. This was not magic, it was simply clever physics, creating a force advantage that made the supernatural seem routine. Another monumental leap was the shaduf, an early crane from Mesopotamia. This clever device used a long, counterweighted beam to lift heavy buckets of water or construction materials from canals and building pits. It was a simple machine that drastically reduced the physical strain of repetitive lifting. Later, Greek engineers refined this concept into more sophisticated cranes, some powered by human treadwheels, which allowed for the precise placement of massive marble blocks in temples and monuments. These tools were never used in isolation. A quarry team used chisels and levers to free a block. Transport crews used sledges and rollers to move it. Then at the construction site, a system of ramps, ropes, and perhaps an early crane would take over to lift it into its final position. Each tool was a link in a continuous chain of efficiency. This evolution was driven entirely by practical problem solving. An overseer watching his teams struggle to lift a cornerstone would not turn to a scientific textbook. He would instead encourage experimentation, perhaps leading to a stronger rope, a better lubricant for the rollers, or a new arrangement of pulleys. Each small innovation, born from the immediate need to overcome a physical obstacle, compounded over generations, creating a legacy of engineering wisdom that enabled the impossible. This brings us to one of the most enduring and debated applications of these simple machines, the intricate ramp systems that may have carried every single block of the Great Pyramid to its skyward destination. The ramps snaking up the pyramid's flanks were more than just slopes. They were temporary mountains built by human hands. These immense earthen causeways, constructed from millions of mud bricks and limestone chips, grew in perfect synchrony with the monument itself, creating a spiraling or zigzagging highway to the sky. Their design was a masterclass in practical physics, balancing the need for a gentle enough slope for teams to pull massive blocks, with the structural integrity to support unimaginable weight without collapsing. A ramp that was too steep became an impossible climb, while one that was too long consumed an unsustainable amount of material and labor to build. Engineers solved this with different designs for different challenges. Straight ramps sufficed for lower levels, but for reaching the soaring summit, a corkscrewing ramp that wrapped around the structure or a clever zigzag design minimized the overall incline, making the grueling ascent feasible. The construction of the ramp was a massive project in its own right, demanding its own dedicated crews who worked constantly to extend the pathway upward and repair the ruts worn by countless stone-laden sledges. Recent discoveries point to an even deeper level of sophistication. Evidence from sites in Egypt suggests some ramps may have incorporated clever counterweight systems. Imagine a heavy container of stone chips descending one side of the ramp, its gravitational pull helping to hoist a fresh block up the other side. This was not brute force, but a calculated application of mechanical advantage, a way to multiply human effort using gravity itself. Once the final capstone was set, the ramps had served their purpose. Their gradual dismantling was the last, carefully managed act of the logistical ballet, the temporary landscape of achievement slowly erased, leaving only the perfect geometric form against the horizon. Yet these temporary ramps were just one part of a much larger, permanent network. The true arteries of empire were the roads and canals that connected quarries to cities across vast distances. These roads were more than just pathways, they were the permanent backbone of an empire, engineered to outlast the rulers who commissioned them. The famous Roman roads, with their deep foundations and cambered surfaces for drainage, were not built for speed but for relentless, heavy-duty transport. A legion could march on a dirt track, but the 50-ton marble columns for a new temple required a highway that would not buckle under the strain. This was a long-term investment in logistics infrastructure, a network so robust that some of its routes are still in use 2,000 years later. This principle of permanent infrastructure extended to water as well. In China, the Grand Canal stands as a testament to this vision, a massive artificial river engineered with sophisticated lock systems. These locks acted as aquatic elevators, raising and lowering barges to navigate changes in elevation, allowing them to carry vast quantities of grain and stone across hundreds of miles of varied terrain. The construction of these networks themselves posed a fascinating recursive challenge. To build a road that could carry stone, you first had to move the stone to build the road. This required temporary, smaller-scale versions of the very logistics systems the finished network was meant to support. It was a cycle of building infrastructure to enable the construction of more and better infrastructure. Once these routes were established, they demanded constant care. Dedicated maintenance crews were a permanent feature of these systems, filling ruts in Roman roads, dredging silt from Chinese canals, and ensuring that the flow of materials never stopped due to a collapsed bridge or a blocked waterway. This ongoing upkeep was a hidden cost, but one that ancient planners understood was essential for the long-term health of their supply chains. The strategic placement of quarries and brickworks reveals another layer of their logistical genius. They were almost always situated as close as possible to these permanent transportation networks, whether a river, a canal, or a major road. This was a deliberate effort to minimize the most difficult and expensive part of the journey, the initial haul from the source to the main artery. By optimizing location, they turned a potential logistical nightmare into a manageable first step. This meticulous planning of routes and networks was only half the battle, however. The other half was understanding that not all materials are created equal, and each substance, from fragile carved stone to heavy metal ingots, demanded its own unique handling and transport method. Each material whispered its own demands to the ancient engineers. Transporting a dense granite block was a completely different challenge from moving a long, fragile timber beam or a column of flawless marble. The very substance being moved dictated the entire logistical approach, from the equipment used to the speed of the journey. Granite and limestone, being incredibly strong and durable, could handle a more robust process. They were often simply rolled onto barges or dragged on sledges without much concern for minor scrapes or exposure to water. This resilience allowed for faster, more efficient transport. Marble, however, was a different story. Prized for its beauty and fine grain, it was also notoriously brittle. A single sharp impact could fracture an entire column, ruining months of quarrying work. To prevent this, teams developed careful packaging techniques, swaddling marble in protective layers of reed matting and straw, and building wooden cradles that distributed pressure evenly during transit. This was logistics with a delicate touch. The movement of wood presented its own unique puzzles. While timber floats, long, heavy beams could easily become waterlogged and sink, or be damaged by constant immersion. Builders countered this by sealing wood with tar to repel water and constructing specialized rafts or floating platforms that kept the precious cargo safely above the waterline. Then there were the high-valued decorative materials, the gold leaf, lapis lazuli, and exotic ebony. Their logistics were less about weight and more about security and preservation. These items were often transported in small, guarded convoys. Their movement kept secret to deter theft, a stark contrast to the very public, massive convoys of stone. This material-specific knowledge was a form of deep, practical wisdom. It meant knowing that fragile materials required a slower, more deliberate pace with frequent inspections, while stable granite allowed for relentless, steady progress. This nuanced understanding, developed over generations of trial and error, ensured that every component, from the mightiest foundation stone to the most delicate inlay, arrived at the construction site in perfect condition. Yet, even the most carefully planned transport route was at the mercy of a far greater force, the turning of the seasons and the rhythms of the natural world. The calendar was not just a tool for tracking time, it was the master schedule for the entire operation. Ancient planners lived by the rhythm of the seasons, aligning their monumental tasks with the predictable cycles of nature. They consulted astronomical charts to forecast the annual flooding of the Nile and meticulously planned the transport of stone to coincide with the river's peak. This was not a passive response to the environment, but an active, strategic partnership with it. During the inundation, when the farmlands vanished underwater and construction on the plateau might slow, the river itself transformed. Its swollen waters reached closer to the building sites, allowing barges carrying the heaviest stones to travel distances that were impossible during the dry season. The very force that halted one aspect of work supercharged another, turning a period of potential delay into a window of maximum logistical efficiency. This synchronization extended to the workforce itself. The same farmers who tilled the land during the planting and harvest seasons became available for national projects when the Nile's flood made their fields untouchable. This created a brilliant cyclical labor model. The state gained access to a massive, temporary workforce without destabilizing the agricultural base that fed the entire nation. The number of workers on a project like the Great Pyramid would have swelled and contracted like a heartbeat, pulsing in time with the seasons. This required incredibly flexible management. Scribes and overseers had to plan for these predictable influxes of labor, assigning them to the most labor-intensive tasks like hauling stones or maintaining ramps before they returned to their farms. Even the choice of transport technology was dictated by the weather. A sledge dragged over wet sand, lubricated by water, moved with a surprising ease that was impossible on dry, gripping dunes. Conversely, wheeled carts required the firm, dry ground of summer to operate effectively. Planners had to be ready to switch methods based on the latest conditions, a testament to their logistical agility. This inherent unpredictability forced the development of another key strategy, the creation of massive storage yards. During the optimal seasons, when quarrying and transport were at their peak, materials would flow in faster than they could be used. These surplus stones were stockpiled in organized areas near the construction site, creating a vital buffer stock. When the high water receded or the summer heat made transport difficult, work did not have to stop. The builders could draw from this reserve, ensuring a continuous, uninterrupted workflow year-round. This was ancient just-in-time delivery, smoothed by strategic foresight. They did not try to conquer nature's cycles with sheer force, but instead learned to dance with them, turning potential obstacles into powerful allies. This intricate dance of men, materials, and seasons was only possible because of another invisible network, one that carried not stone but information. The true nervous system of this entire operation was not carved in stone, but flowed along pathways of information. While thousands of workers moved physical materials, a parallel network of messengers moved something equally vital: knowledge. Runners carried critical updates between distant quarries, bustling river docks, and the ever-rising pyramid face, creating a real-time information web that kept the entire project in sync. This communication network was the only way to prevent catastrophic delays. A message from the quarry foreman about a newly extracted block would trigger the preparation of a transport crew and a barge at the river. A report from the ramp builders about a structural issue could be relayed back to the overseers, who might temporarily reroute stone deliveries. This constant flow of data allowed for adaptive management, where a problem in one part of the chain could be quickly addressed by adjusting the others. For immediate line-of-sight coordination, teams used visual signaling. Smoke plumes from high hilltops or a system of flags could convey simple, pre-arranged messages across vast distances in an instant, directing a barge to a different dock or calling for extra workers at a specific location. These methods provided the swift, urgent communication needed to keep daily operations flowing smoothly. But for more complex information, something more permanent was required. The development of writing systems was a logistical revolution in its own right. Scribes used clay tablets and papyrus scrolls to create the project's memory, meticulously recording inventories of tools, assignments for work gangs, and detailed reports of problems encountered. A single tablet could list the expected delivery of 200 limestone blocks from a specific quarry, allowing managers to anticipate needs and allocate resources days or weeks in advance. This written record created accountability and precision, transforming the chaotic movement of men and materials into a managed, predictable process. These different communication methods worked together in a sophisticated feedback loop. A visual signal might alert officials to an issue, a runner would carry the detailed report, and a scribe would permanently record both the problem and the solution enacted, building an institutional knowledge base for future projects. This evolution from simple shouts to complex record-keeping shows a clear trend. As construction projects grew more monumental, the management of information had to keep pace. The entire endeavor rested on this invisible foundation of coordinated knowledge. Yet, for all this communication to have meaning, every message, every order, every inventory list had to speak a common, precise language. This required a universal system of mathematics and measurement that could translate grand visions into actionable, exact instructions. A shared language of numbers and measurement was the silent contract that held the entire operation together. Without it, a block quarried in the south would never fit the space prepared for it in the north. This is why the development of standardized units like the Egyptian cubit was so revolutionary. It was not just a ruler, it was a universal key. A quarry worker, a transport foreman, and a master builder, all separated by miles, could work in perfect harmony because they all used the exact same measure. This consistency transformed construction from a chaotic gamble into a predictable, repeatable process. Ancient mathematics provided the mental machinery to turn these measurements into actionable plans. Egyptian and Babylonian mathematicians developed sophisticated geometric and algebraic methods that allowed planners to perform incredible feats of calculation. They could determine the exact volume of a stone block to estimate its weight, a critical piece of information for deciding how many workers were needed to pull it or what size barge would be required to float it. They calculated the angles and forces involved in ramp construction, ensuring these temporary mountains were both stable and climbable. This was not abstract academic exercise, it was mathematics applied to the most pressing physical problems of their time. This precision had to be translated from parchment to the real world, and that required a toolkit of ingenious instruments. The simple plumb bob, a weighted string, became an indispensable tool for establishing true vertical lines, ensuring that walls rose straight and true. Leveling instruments, often just a water-filled trench, allowed workers to create perfectly flat foundations and ramps, a non-negotiable requirement for the stable movement of heavy sledges. Sighting tools, precursors to the modern theodolite, enabled surveyors to align massive structures with celestial bodies or lay out vast construction sites over uneven terrain with breathtaking accuracy. These tools meant that a block shaped miles away would slide into its designated spot with a satisfying finality, the result of mathematical foresight made physical. Yet all this planning would be useless without accountability. This is where early accounting systems emerged as the memory of the project. Scribes kept meticulous records on clay tablets and papyrus, tracking every chisel used, every work gang's daily progress, and the efficiency of each transport crew. They noted if a team moved only 10 blocks in a week when the plan called for 15, prompting an investigation into a broken sledge or a depleted water supply. This was performance measurement in its most ancient form, creating a feedback loop that allowed managers to identify bottlenecks, reallocate resources, and keep the entire logistical machine running at peak efficiency. With these mathematical foundations, planners could do something that feels remarkably modern. They could forecast. By knowing the volume of the pyramid and the average output of their workforce, they could estimate project timelines and resource needs with surprising accuracy. They could predict how much grain would be needed to feed the workers next season and how many barges would be required during the next Nile inundation. This integration of mathematics into logistics was the intellectual engine of the operation, the invisible framework that gave form to ambition. Yet, the specific shape of that ambition was always molded by the land itself, leading civilizations separated by continents to develop brilliantly unique answers to the same fundamental question of how to move the earth. Every civilization faced the same fundamental challenge, but the earth offered each a different set of tools. The Egyptians built their logistical empire on the predictable, life-giving rhythm of the Nile, a single, dominant corridor of power. Their entire system, from the timing of stone deliveries to the management of labor, was synchronized with the river's annual flood, creating a model of centralized, rhythmic efficiency. The Romans, by contrast, built an empire of logistical integration. Their challenge was not one river, but 1,000 different landscapes, from the deserts of North Africa to the forests of Britain. They could not rely on a single natural force, so they overlaid the entire Mediterranean world with a man-made network of robust roads and sea routes, creating a flexible, adaptable system designed to standardize transport across incredible diversity. Then, in the dense jungles of Mesoamerica, the Maya achieved their monumental constructions under a completely different set of rules. Without the wheel, without draft animals, and without vast metal tools, their entire logistical system was powered by human ingenuity alone. They moved massive limestone blocks using rollers, levers, and immense ramp systems, all powered by coordinated teams of workers. Theirs was a triumph of social organization over technological absence, proving that a well-organized human network can be the most powerful machine of all. High in the Andes, the Inca engineers faced perhaps the most daunting terrain of all, the sheer, vertical world of the mountains. They could not build straight Roman roads across peaks and ravines. Instead, they mastered the landscape by weaving into it, constructing stairway roads that climbed impossible slopes and legendary suspension bridges made from woven grass that spanned dizzying chasms. This allowed them to transport stone and other materials across a fractured empire, building mountaintop citadels that seemed to defy gravity itself. At first glance, these systems could not be more different, one flowing on water, one marching on paved roads, one climbing stairways, and one pushing through jungle. Yet, if you look closer, universal principles of logistics emerge from all of them. Each civilization developed a clear hierarchy of labor with specialized roles and overseers. Each invested heavily in route planning, whether that route was a river, a road, or a mountain trail, and each displayed a profound understanding of resource management, knowing that the true project was not just moving stone, but sustaining the people moving it. These common threads reveal a shared human genius for solving physical problems through organization and foresight. This raises a compelling question that connects these ancient systems to our modern world. How did these principles scale up from a single temple to an entire city? And what can that teach us about managing complexity today? The leap from a single temple to an entire city of monuments required a new kind of logistical imagination. Early, smaller projects were the essential proving grounds, the workshops where techniques were refined and organizational models were tested. A successful method for moving stones to a provincial tomb could be studied, improved, and then codified into a standard procedure for a national project 10 times its size. This process of standardization was the true catalyst for scaling up. It meant that a master builder sent to a new city could implement the same ramp designs, the same crew structures, and the same measurement systems that had proven successful elsewhere, creating a repeatable blueprint for monumental achievement. This replication of success hinged on the creation of specialized roles that transcended any single project. Ramp engineers became experts in soil mechanics and incline management, their knowledge applicable whether building a pyramid or a vast temple complex. Transport coordinators understood how to move materials across both river and desert, and their expertise could be deployed to manage multiple supply chains running simultaneously to different construction sites. These were not temporary laborers, but career professionals whose deep, focused knowledge created pockets of excellence that could be plugged into any project, anywhere. As operations scaled, the old methods of record-keeping were no longer sufficient. Tracking materials for one structure was manageable, but coordinating the flow of stone, timber, and workers across several massive sites, often separated by hundreds of miles, demanded an entirely new level of documentation. Scribes developed elaborate accounting systems, creating ledgers that could track inventory levels at distant quarries, the productivity of work gangs at half a dozen locations, and the scheduled arrival of barges from upriver. This paperwork was the central nervous system of the scaled-up operation, allowing managers in the capital to have a real-time understanding of progress and problems across their entire domain. The true genius of this scaling, however, lay in its modular design. Each major construction site operated with a degree of autonomy, with its own local managers, its own dedicated workforce, and its own support infrastructure. This prevented a bottleneck of decision-making at the center. Yet, these semi-independent modules were all bound together by a central plan. The capital ensured that resources were allocated fairly, that specialized experts could be rotated between sites as needed, and that all projects adhered to the same overarching standards and timeline. It was a delicate balance of local initiative and central control, a system that allowed for immense complexity without collapsing under its own weight. This ability to manage such vast, simultaneous endeavors reveals a level of administrative sophistication we often assume is unique to the modern corporation. The entire machine, however, from the quarry worker to the master scribe, was powered by an economic engine of staggering proportions. The silent engine driving every stone and every meal was a sophisticated economic system, a financial architecture that funded ambition for generations. These decades-long projects were not powered by sheer will alone, but by vast flows of wealth channeled through taxation, tribute from conquered lands, and generous donations to religious institutions. In Egypt, the pharaoh's granaries and treasuries, filled with the agricultural surplus of the Nile Valley, became the project's bank account. Every load of stone, every loaf of bread for a worker, represented a withdrawal from this centralized economic reserve. Yet this was not a blank check. Ancient accountants developed meticulous systems to track these expenditures, inscribing on papyrus the cost of materials, the size of work gangs, and the rations distributed. This was not merely bookkeeping, it was a powerful tool for preventing waste and ensuring that the state's immense investment was not squandered. The development of standardized currency, first in the form of weighted metal and later coins, revolutionized this process. It allowed for more fluid and complex transactions, enabling a foreman to pay a team of specialist carvers from a distant city or a royal agent to purchase a shipment of rare cedar wood from a foreign merchant. This monetization created a more flexible and scalable economy capable of supporting such vast endeavors. The very choice of materials reveals the strategic priorities embedded in this economic thinking. Why would Egyptian pharaohs transport granite from quarries hundreds of miles upriver when local limestone was abundant? The answer lies in the stone's symbolic power. Granite, with its immense durability and striking color, was reserved for the most sacred elements of a tomb, meant to last for eternity. The extraordinary cost of its transport was not seen as an extravagance, but as a necessary investment in religious and political legacy. This economic framework also created powerful incentives for innovation. There is evidence from worker villages that more skilled crews received larger rations or other rewards. An overseer who devised a faster method for loading barges or a more stable ramp design might be promoted, his idea then adopted across the empire. The entire logistical machine was lubricated by an economic understanding that efficiency and clever problem-solving had tangible value. This reminds us that these wonders were not just feats of engineering, but also of political will and social contract, funded by the collective resources of a civilization. The success of this entire enterprise, however, relied on something even more fragile than gold or grain: the careful preservation of hard-won knowledge across the centuries. A master builder's most vital blueprint was not for a ramp or a temple, but for the mind of his apprentice. This knowledge, the accumulated wisdom of moving mountains, could not be stored in a granary or locked in a treasury. It lived in the hands and the memories of skilled individuals, passed from one generation to the next through the patient rhythm of daily work. An experienced quarryman did not give his student a written manual on how to spot the perfect fracture line in a granite face. Instead, he placed the younger man's hands on the stone, guiding his chisel, teaching him to feel the rock's hidden language through the vibrations in the tool. This was a living library of technique, where every correct swing of a hammer and every properly tied knot was a sentence in an ongoing story of human ingenuity. Oral tradition and practical demonstration were the primary engines of this transmission, creating an unbroken chain of expertise that could span centuries. This knowledge was not just technical, it was cultural. The precise rituals for laying a foundation stone or the ceremonial songs sung by workers hauling a massive obelisk were not mere superstition. They were mnemonic devices, rhythmic and ritualized practices that encoded complex logistical sequences into the community's very identity. Guilds and family-based craft lineages institutionalized this process, creating closed circles of experts who guarded their methods fiercely, ensuring that the secrets of moving 50-ton blocks remained a protected, valuable asset. The development of writing systems, however, marked a revolutionary shift. It allowed for a new kind of precision. A clay tablet from ancient Mesopotamia does not just list supplies, it provides step-by-step instructions for building a specific type of boat, detailing the exact quantity of bitumen needed to make it watertight. Egyptian papyri contain mathematical problems for calculating the slope of a ramp or the number of workers needed to drag a statue of a given weight. These were the first technical manuals, freezing fluid knowledge into a permanent form that could be studied, copied, and sent to a construction site 100 miles away. This written record created a feedback loop across time. A scribe could record that a particular ramp design had failed under a certain load, and a planner 50 years later, reading that account, would know to avoid that mistake. This is how we see clear evidence of gradual, cumulative improvement in the archaeological record. The stone-moving techniques used for the later pyramids are more refined than those for the earliest ones. The block sizes are more standardized, the quarrying marks more efficient, the pottery jars used for water transport are better designed for stacking on boats. Each project became a living laboratory, its successes and failures meticulously informing the next. This was not a sudden leap, but a slow, relentless compounding of small innovations. A better rope fiber discovered in one era, a more effective sledge lubricant in another, a more stable ramp design in a third. All these tiny advances were preserved and integrated into the standard toolkit. This ability to preserve and build upon hard-won knowledge, to prevent it from being lost with the passing of each master craftsman, is one of humanity's most profound organizational achievements. It transformed individual cleverness into a permanent cultural resource, a collective intelligence that grew smarter with every passing generation. This intricate web of practical knowledge, however, was deeply woven into a larger tapestry of belief, where the divine and the logistical were often one and the same. The movement of a single stone could be a sacred act, a procession witnessed by the gods. In ancient Egypt, the transport of an obelisk from the quarry to its final resting place at a temple was not just a technical operation, it was a profound religious event. Priests walked alongside the massive stone, conducting ceremonies and making offerings to deities at each stage of the journey, transforming a grueling physical task into a mobile ritual. The very path the stone traveled was considered hallowed ground, a temporary sacred space created by the act of moving a piece of the divine earth. This spiritual dimension infused the entire logistical machine with a purpose that went far beyond mere construction. The timing of these operations was often dictated by the heavens. Builders did not just wait for the Nile flood, they coordinated the movement of cornerstone blocks with specific celestial events, like the rising of the star Sirius. They believed that aligning the transport with these powerful moments would imbue the stone and the entire structure with cosmic energy and divine favor. This was logistics synchronized with the cosmos, where a calendar of the stars became the project's master schedule. This cultural context reshapes our understanding of the workforce. For many individuals, contributing to a temple or pyramid was not a burden forced upon them, but an act of deep religious devotion and civic pride. In societies like ancient Egypt and Mesoamerica, participating in such a project was a way to earn spiritual merit and honor one's community. This created a powerful, intrinsic motivation that money or rations alone could never provide. A worker dragging a sledge under the blistering sun might see himself not as a laborer, but as a participant in a grand ritual that connected his people to the gods. This cultural framework provided a resilient psychological foundation for projects that spanned entire lifetimes. It helped sustain morale through immense hardship, fostering a shared identity and a collective sense of purpose that could be passed from father to son. This explains the extraordinary effort invested in structures that had no practical, day-to-day utility in the modern sense. A pyramid was not a housing complex. A ziggurat was not a marketplace. Their primary function was spiritual and symbolic, serving as a permanent bridge between the human and the divine. The immense logistical effort was seen as a worthy offering, a physical manifestation of a society's faith and identity. This cultural engine, however powerful, was not infallible. Even the most spiritually motivated and brilliantly planned systems could be brought to a halt by the unpredictable forces of nature or human error. Even the most brilliant blueprint could shatter against an immovable reality. An obelisk-laden barge caught on a hidden sandbar would halt the entire ceremonial procession, demanding immediate, on-the-ground ingenuity. Archaeological sites are littered with the ghosts of these logistical failures, stories told in broken stone and abandoned pathways. A half-finished temple wall in Mesopotamia shows a clear change in the type of stone used partway through construction, a silent testament to a supply chain that broke down, forcing builders to find a local substitute. A collapsed ramp at the base of an Egyptian pyramid, its mud-brick structure unable to bear the relentless weight, would have required a rapid redesign, perhaps a wider base or a gentler slope, implemented under the pressure of a looming deadline. These were not signs of poor planning, but proof of a system's resilience, its ability to learn and evolve in real time. Environmental crises were the ultimate test of this flexibility. An unexpected drought that lowered the Nile would strand fleets of stone-carrying barges far from their destination. The response was not to wait for the rains, but to improvise. Engineers would reroute transport overland sooner than planned, mobilizing thousands more workers and their sledges to drag the stones across the desert. Conversely, a flash flood could wash away a carefully prepared causeway, requiring crews to rebuild the road with stronger retaining walls, incorporating the lesson of that failure into the next project's design. This adaptive capability was baked into the system through strategic redundancy. Wise planners never relied on a single quarry. If political unrest or a rockfall closed one source of limestone, a secondary quarry, perhaps of slightly different quality, would be activated to keep the flow of materials constant. They developed multiple transport routes, knowing that a primary canal might silt up or a mountain pass could become blocked by a landslide. Even labor was managed with backups, drawing from different regions to ensure that a local illness or harvest would not completely halt progress on a national project. The most elegant solutions often emerged from cross-disciplinary thinking. A shipwright's knowledge of ropes and pulleys for managing sails could be adapted to create a more effective rigging system for lowering heavy blocks into place. The architectural understanding of how to distribute weight in a vaulted ceiling might inspire a new method for stacking stones on a transport barge to prevent capsizing. This was not a collection of isolated trades, but a vibrant ecosystem of shared knowledge, where a breakthrough in one field could solve a stubborn problem in another. These ancient logistics were not a rigid, predetermined machine, but a living, breathing organism that learned from its stumbles and grew stronger with every challenge it overcame. Yet, moving millions of tons of stone and sustaining thousands of workers for decades inevitably left a profound mark on the landscape itself, a footprint we are only now beginning to fully understand. The very landscape bore the weight of these ambitions, its shape permanently altered by the relentless demand for resources. Vast forests surrounding construction sites slowly receded, their timber consumed for the endless need of ramps, sledges, and tools, and to fuel the fires of bakeries and brick kilns. This local deforestation created a cascading effect, changing microclimates and forcing logisticians to seek wood from ever greater distances, which in turn created new, longer supply chains to manage. The ecological footprint extended far beyond the loss of trees. Quarrying operations scarred the earth, leaving behind immense pits and mountains of stone debris. The constant traffic of sledges and carts along established routes compacted the soil and altered water drainage patterns, while the sprawling worker settlements placed immense strain on local water tables and sources of food. These were not isolated projects, but forces of environmental engineering that reshaped the world around them. Yet within this dynamic, we find evidence of a remarkable foresight. Some civilizations practiced a form of ancient sustainability. In regions dependent on wood, they developed coppicing, a method of carefully harvesting tree growth in cycles to ensure a continuous, renewable supply rather than clear-cutting entire forests. Quarry masters sometimes deliberately rotated their sites, allowing exhausted ones to rest and, in a way, heal, while new ones were opened, demonstrating a long-term understanding of resource regeneration. The management of water became about more than just transport. Engineers had to contend with the erosion and sedimentation caused by their own earthworks. They constructed intricate systems of ditches and retaining walls to control runoff from denuded landscapes, preventing their carefully built ramps and roads from being washed away by a sudden rain. This delicate dance with the environment is visible in the very location of industrial centers. Planners made strategic choices, sometimes accepting a longer, more difficult transport route from a quarry if it meant preserving a vital woodland or a fragile watershed closer to the construction site. They were constantly balancing the immediate need for materials against the long-term health of the local environment that sustained their workforce and their project. These interactions reveal that ancient logistics was not a conquest of nature, but a complex negotiation with it. The systems they built existed within a web of ecological constraints that ultimately shaped their methods, their costs, and their very identity over centuries. Every scrape of a chisel and every footstep of a worker left a mark on the earth, and it is through the careful study of these marks that our modern understanding is being radically rewritten. The quiet hum of a ground-penetrating radar unit reveals a hidden world beneath the sand. This modern technology acts like a second sight, uncovering the ghostly impressions of ancient causeways and loading docks that have been invisible for millennia. These are not just paths, they are the data streams of a forgotten supply chain, suddenly made visible. Archaeologists are no longer just studying the monuments themselves, but the intricate fingerprints of the systems that built them. A closer look at the stone blocks of the Great Pyramid, for example, reveals tool marks that tell a specific story. The angle of a chisel cut or the pattern of abrasion on a surface can indicate whether a block was dragged on a sledge, rotated on rollers, or perhaps even levered into a specific position using a clever counterweight system. Each mark is a word in a long-lost instruction manual. Some of the most dramatic findings have completely rewritten our textbooks. The long-held image of a single, straight ramp towering over a pyramid has been complicated by evidence of sophisticated internal ramp systems. Imagine a spiraling corridor deep within the growing structure itself, a hidden highway that allowed workers to pull blocks from the inside, a solution that was both elegant and largely invisible in the finished product. At the same time, the discovery of massive, purpose-built harbors on the Red Sea coast, dedicated solely to receiving limestone blocks from distant quarries, shows a level of specialization we never fully appreciated. These were not simple river docks, but the ancient equivalents of modern industrial ports, designed for one thing: the efficient transfer of stone from water to land. Scientific analysis has added another layer of understanding. By studying the layers of sediment in a dried-up canal, researchers can determine how often it was dredged and how heavily it was used. Satellite imagery, able to detect subtle variations in plant growth, can trace the faint outlines of ancient roads and pathways leading from quarries that are completely lost to the naked eye. 3D modeling then allows us to virtually test these routes, simulating the effort required to move a 50-ton block along them, turning theoretical ideas into practical, measurable experiments. Perhaps the most humanizing discoveries come from the remains of the worker villages. The analysis of animal bones and grain storage pits paints a detailed picture of their diet, revealing a caloric intake that sustained immense physical labor. The layout of their homes and workshops speaks to a highly organized community, with clear zones for different trades and a social structure that supported this monumental effort. These settlements were not temporary camps, they were the beating heart of the logistical operation, and every artifact found there adds a crucial piece to the puzzle of how they lived and worked. Each of these discoveries, from a radar image to a broken pottery shard, is a correction to our historical model. They remind us that our understanding is a living thing, constantly being refined. Just when we think we have the answers, the sand shifts and reveals a new question. This evolving picture of the past holds surprising relevance, raising a compelling possibility for our own time. What if the solutions to some of our most complex modern supply chain challenges are not found in the future, but have been waiting in the past, quietly preserved in stone and earth for thousands of years? These ancient logistics systems are not just relics, they are a living library of solutions for our modern world. A supply chain manager today, wrestling with a port congestion crisis, might find a surprising answer in the way Roman road crews maintained their vital arteries for centuries, preventing small problems from becoming catastrophic blockages. The principle of redundancy, so clear in the ancient practice of maintaining multiple quarries and transport routes, is a powerful lesson for our era of hyper-efficient, just-in-time manufacturing, where a single disruption can halt a global industry. Ancient systems were built with resilience at their core, designed to bend rather than break under the pressure of drought, political unrest, or simple human error. This historical perspective reveals that our relentless pursuit of maximum efficiency can sometimes create immense fragility. Perhaps the most profound lesson is the ancient focus on the human element. The bakeries and infirmaries of the Giza worker villages were not just amenities, they were a strategic recognition that a healthy, motivated workforce is the ultimate engine of productivity. This human-centered model offers a compelling alternative to modern systems that sometimes treat labor as just another input to be optimized, reminding us that caring for people is not separate from logistics, it is the foundation of it. Furthermore, the ancient choice to work with natural cycles, like the Nile's flood, provides a powerful blueprint for sustainable logistics today. Instead of fighting the environment with immense energy costs, they used its inherent forces to their advantage, a concept that could inspire greener supply chains that partner with nature rather than plunder it. The modular organization of ancient work crews, operating with autonomy under a central vision, is a direct precursor to modern distributed teams and cloud-based operations. It proves that coordination does not require constant top-down control, but can thrive on clear standards and local initiative. All of this points to a humbling truth. Advanced logistics does not always demand the latest technology. It can emerge from clever organization, deep practical wisdom, and a profound understanding of the materials, the people, and the world you are working with. Yet, for all we have learned, the full picture of how these systems operated remains tantalizingly out of reach, leaving us with enduring mysteries that continue to challenge our assumptions and fuel our curiosity. Even with all our discoveries, fundamental questions remain stubbornly unanswered. The sheer scale of some ancient transport achievements continues to baffle experts, creating lively debates in academic circles. Take the colossal Thunderstone, a single block of granite weighing over 1,000 tons, moved across Russia in the 1700s to serve as the pedestal for a statue of Peter the Great. Contemporary accounts describe a complex system of bronze spheres acting as ball bearings in frozen metal tracks, a method that seems almost fantastical, yet it worked. How this was managed without modern metallurgy or machinery remains a topic of intense study and speculation. Similarly, at the ancient site of Baalbek in Lebanon, 3 monoliths known as the Trilithon stones, each weighing an estimated 800 tons, sit perfectly fitted in a Roman temple foundation. The quarry for these giants lies nearly a mile away, and the path includes a slight incline. The method used to transport them is a complete mystery, with no surviving records or clear archaeological evidence to point to a definitive solution. These are not isolated cases, they are profound reminders of gaps in our historical knowledge. The administrative coordination for projects spanning multiple generations is another deep puzzle. We understand the basic hierarchy of overseers and workers, but how did they maintain morale and precision over 60 or 80 years, a time frame longer than a single human lifetime? How were complex instructions and architectural adjustments communicated across a rotating, seasonal workforce without the project losing its core vision? The written records we have are fragmentary, leaving the day-to-day human dynamics of these mega projects largely to our imagination. Perhaps the most telling mystery is the recurring pattern of knowledge loss. Advanced logistical techniques, like the precise counterweight systems possibly used in pyramid construction or the Roman recipe for ultra-durable concrete, simply vanished for centuries after those civilizations declined. This disappearance and subsequent reinvention of methods, a cycle of forgetting and rediscovering, suggests that this hard-won practical wisdom is incredibly fragile. It depends not on libraries, but on living communities of practice that can be scattered by war, famine, or social collapse. These unresolved questions are not failures of archaeology, but guideposts for future research. They highlight the boundaries of our current understanding and challenge us to keep looking. The very existence of these mysteries proves that the ancient world still has profound secrets to share, and that the most exciting discoveries may still lie ahead of us. This is where the story turns from interpreting the past to actively recreating it, as researchers roll up their sleeves to test these age-old puzzles with their own hands. The ground shakes as a multi-ton block of limestone inches forward, not by machine, but by the synchronized pull of dozens of volunteers. This is experimental archaeology in action, a field where theories are tested not in libraries, but with sweat and rope and timber. Modern teams have constructed full-scale replicas of ancient sledges, using only period-appropriate materials to move massive stones across prepared causeways. In one famous experiment, researchers successfully transported a concrete obelisk weighing over 30 tons using a wooden sledge and a path lubricated with water, proving the fundamental physics of the Egyptian method was sound. Yet the true revelation was not the success, but the stumbling blocks. They discovered that the type of wood used for the sledge runners was critical, that the water had to be applied in just the right quantity, and that the rhythm of the pulling teams was everything. A single voice out of sync could halt the entire immense weight, a visceral lesson in the coordination required of ancient foremen. Another project focused on ramp construction, building a scaled earth and rubble ramp to test its stability under the constant stress of heavy loads. The team quickly learned that the internal structure of the ramp, its layers of compaction, was far more important than its outward slope. A poorly compacted section would slump under the weight, creating a dangerous rut that could trap a sledge and injure the crew. This hands-on work uncovers the silent, practical knowledge that was never written down, the kind of wisdom an experienced worker would pass to his apprentice through demonstration, not dictation. The sheer physical toll of these experiments offers a profound respect for the ancient workforce. After just a few hours of pulling, modern participants speak of a deep, systemic fatigue that no gym workout can replicate. This experience highlights the critical importance of those ancient bakeries and breweries, the logistical support that provided the calories needed to fuel such back-breaking labor day after day for decades. When an experiment succeeds, it demonstrates that the ancient methods were not only possible but often elegantly efficient with the technology at hand. When an experiment fails, however, it is just as valuable. A snapped rope or a crumbling ramp corner forces a re-evaluation, pointing to a missing piece of the puzzle, perhaps a forgotten technique like a specific type of rope weaving or a method for soil stabilization using gypsum. These tangible tests bridge the gap between our abstract calculations and the gritty reality of the past, revealing a culture that solved immense physical problems through collective, embodied intelligence. This physical process of moving stone, however, was often far more than a simple engineering task. It was imbued with layers of meaning that transformed labor into ritual and a block of stone into a sacred object. A stone's journey was a reenactment of the sun's voyage across the sky. When Egyptian crews hauled an obelisk from quarry to temple, they were not merely moving granite, they were guiding a sliver of solidified sunlight to its eternal home, a ritual that mirrored the celestial cycles they held sacred. The very path the stone traveled was often deliberately aligned with astronomical events, turning a geographical route into a cosmic highway. Materials were not chosen for convenience alone. A pharaoh's insistence on red granite from a quarry 500 miles upriver was a political statement carved in stone, a tangible claim of sovereignty over that distant territory. The stone itself became a piece of that conquered land, physically integrated into the heart of the capital, a permanent symbol of power and unification. This symbolic value justified immense logistical effort, explaining why a simpler, local alternative was never an option. The transport process itself was frequently a grand public ceremony. Records from Mesopotamia describe the movement of a divine statue as a multi-day festival, with priests anointing the statue at designated stations along the route and communities offering food and music as it passed. Each pause was not a delay, but a necessary ritual that infused the journey with spiritual significance, transforming a logistical operation into a mobile act of worship. This deep interconnection between the practical and the symbolic reveals the true complexity of ancient logistics. It was never just about moving weight, it was about moving meaning. The most efficient path was not always a straight line, but the one that carried the most cultural power. This intricate fusion of cosmic belief and earthly effort created a resilient, multi-layered purpose that sustained these projects for generations. The legacy of these integrated systems did not vanish with the last pyramid or Roman road, however. Their core principles quietly filtered through the centuries, resurfacing in unexpected ways to shape the very foundations of our modern world. Medieval cathedral builders often looked back to the Roman aqueducts standing in their own landscapes, marveling at the sheer scale and durability. They did not have the complete blueprints, but they absorbed the core principles, especially the Roman mastery of load-bearing arches and the strategic use of permanent road networks for moving stone. This was not a direct handoff of knowledge, but a slow, persistent echo. The organizational genius of ancient logistics never truly vanished. It was preserved in scattered monastic manuscripts, in the oral traditions of stonemason guilds, and in the very ruins that later engineers would study with a sense of awe and competitive spirit. During the Renaissance, a renewed fascination with classical texts led to the rediscovery of Vitruvius's writings on architecture and engineering, which detailed Roman methods for hoisting heavy weights and managing large workforces. These rediscovered ideas directly influenced the ambitious domes and palaces of the era, proving that the old solutions still held immense power. The Roman road network itself became the literal foundation for medieval trade and transport, its routes so intelligently laid that they remained in use for over 1,000 years, a permanent infrastructure shaping the flow of European history. Even Egyptian quarrying techniques, with their precise channeling and levering of stone, can be traced in the methods used to extract marble for Italian Renaissance sculptures. The parallels in organizational models are even more striking. The ancient practice of dividing a massive project into specialized teams, each with a foreman reporting to a central overseer, is a direct precursor to the structure of a modern construction site. The meticulous records kept by Egyptian scribes, tracking daily progress and resource consumption, prefigure the Gantt charts and resource allocation software used by project managers today. They understood the fundamental truth that any grand vision, whether a pyramid or a software launch, depends on a hidden framework of planning, scheduling, and accountability. This historical continuity reveals something profound about human ingenuity. These ancient systems were not isolated miracles. They were foundational developments in our collective ability to manage complexity, to coordinate thousands of people toward a single, breathtaking goal. Their enduring influence, felt in the arches of a Gothic cathedral and the logic of a modern supply chain, is the ultimate testament to their sophistication. They built more than monuments, they built the very concepts of large-scale organization that our world still relies upon. These ancient logistics were far more than primitive engineering. They were a complete philosophy of problem-solving. The intricate dance between the Nile's flood and the movement of stone reveals a society that saw partnership with nature as the ultimate form of efficiency, a lesson in sustainability we are only now relearning. The mountain stairways of the Inca and the Roman road networks prove that the most resilient systems are those woven into the very fabric of the landscape, not imposed upon it. Each of these civilizations achieved the monumental not through isolated acts of genius, but through a holistic approach that wove together engineering, astronomy, cultural belief, and profound social organization. The true wonder, then, is not the pyramid or the temple standing in the desert, but the invisible network of knowledge and coordination that allowed it to rise. This legacy challenges our modern obsession with technological novelty, reminding us that the most advanced solutions are often rooted in timeless principles of clarity, foresight, and respect for human capacity. As new archaeological techniques uncover lost harbors and hidden ramps, our understanding of these systems continues to evolve, proving that the past still holds secrets capable of inspiring our future. We now see these ancient wonders not as silent tombs, but as the final, frozen expression of a dynamic and brilliant logistical machine. Which of these forgotten systems most reshapes your view of the ancient world, and what could its principles teach us today?